aircraft engine. As you can see, these are the different parts of the aircraft engine. I think you must be very well aware of all the parts. So if you look at the front side of the engine, this is the fan blades are there. Okay, so these fan blades are made of composite. Okay, and the rest of the engine is all made of the titanium alloys or metal alloys, different metal alloys. So now composite community, they are trying to put different parts into the aircraft engine. So to start with that process, they already converted this all these fan blades at the front side into composites. Also the fan platform at the front side, also fan platform. Fan platform means the fan blade where it's going to sit there. There is some special component there, which is called platform. So that platform is also made of composite nowadays. This spinner nose also made of composite. Then this, if you look at the fan case, this fan case is also made of composite nowadays. So going forward with that, incorporation of composite into the aircraft engine. So the next target was the booster blade. So this area here is a low pressure compressor actually, this area. And there are very small blades there. You can see the size of the blade, very small blades are there. So these blades are currently made of this titanium alloys. Okay. So this is a kind of feasibility study whether we can actually incorporate this composites into this booster blade. Okay. The thing is, as you go in the right direction here, the temperature increases a lot. But in the booster stage compressor, temperature is still not that high, so we can still get away with the temperature requirements, and we can still use the composite here in booster blade. Okay. So let's talk about that. Yeah, what is the function of booster blades? Of course, it is part of the low pressure compressor, and it increases the airflow intake and also increases the centrifugal effect to boost the pressure. And as you boost the pressure, okay, so ultimately it increases the power output and performance of the aircraft engine. Okay, booster blades. So what is the booster blade? How does it look like? So as you can see, the booster blade, actual booster blade model is shown there. Okay, and separately it looks like this. But when you fit into the rotor assembly there, as you can see, you fit into the rotor assembly and you see this different blades like they are fitted like this along with the platform. So the blade is integral with the platform here, as you can see, this platform. The blade is integral with this platform here, and the whole thing is made of metal right now. So as you can see, these are fitted like this one by one, and they are part of the rotor assembly. Okay, so basically, can we convert this metal booster blade into composite? And if you want to do that, then what are the advantages? First thing, of course, is the weight saving. There will be weight saving. If you compare carbon composite weight with the titanium weight, of course, there is a weight saving. And even small amount of weight saving also gets converted into a large amount of cost saving in the aviation business, of course. So the design criteria for this booster blade is what, basically? So as you can see, if you look at the figure here, this front side composite fan blades, they are all designed based on the burst drive. So bird is coming and hitting on this composite fan blades, okay. And then composite fan blades, they have to sustain under that bird heat, okay. But after that, there's a booster. So what happens is, as you can see, there is a gap between these composite blades. There's a gap. So suppose the part of the bird, suppose it escapes through this gap and goes further and hits the booster blade. So that is the requirement here. So requirement is the part of the bird is coming and hitting the booster blade. Okay. And under this kind of loading, the booster blade should survive. Okay. The part of the bird is coming and hitting the booster blade. So this is again a burst strike, but not the full bird. Part of the bird is coming and hitting the blade here, and the blade has to survive. This is the requirement, which is very critical. Okay. So how to define the requirement? So 165-gram bird hitting with approximately 110 meter per second velocity at a 32-degree angle. This angle is coming from that design only, because if you look at the engine cross section, so if the bird is escaping through the gap between the fan blades and coming and hitting, it comes at 32-degree angle. Okay, and it is hitting uh, on the booster blade, but blade is rotating. Okay, so it is hitting at the relative velocity there. It's hitting the it's hitting the rotating blade. Okay, so that's what is the requirement here. Okay, so what did we do? What did we do? What was our approach? Okay, so what we decided is this booster blade is approximately like, let's say, total 1 inch long and let's say 4 inch wide or something like that. It's not that big. It's a small one. Okay, and it does look like a plate. Okay, so we decided to start with a plate, composite plate. Okay, so we'll design and make the composite plate simulating the booster blades, and then we use the optimized layup of laminated composite. Of course, we'll be using carbon epoxy because the kind of requirement they have bus strike, only carbon composite can sustain there. No other composite can sustain here. So test the plates under bus strike, of course, and create the API models of the plates and do bus strike analysis, and then compare the experimental and simulation results, and then further optimize the design for different layups like materials, layups, and different bird size and velocities. Okay. And whatever understanding we'll get out of all these things, we'll be using for actual design of the booster plates, composite booster plates. Okay. So this is the approach. So we started with this plate bus strike simulation. So as you can see, we model a plate and we model a bird. So there is this is done in LS-Dyna, by the way. Okay, there is a explicit dynamic simulation, bird hitting at very high velocity and onto the plate. Okay, so the impact could be a transverse impact, or impact could be some oblique impact, like hitting at some angle, or impact could be just sliding on the plate like that. So different directional impact we studied here. So as you can see, the plate model looks like 5 inch by 2.7 inch by 16 ply stick. So it's a laminate composite. So as it is a laminate composite, so we made it like 16 ply stick. Okay, and of course the plate metal property is M78551 carbon epoxy, and two layers are tried here: the actual fan-blade layer and the quasi-isotropic layer. So actual fan-blade layer is very complicated, but we kind of generalize it for our use. And the quasi-isotropic, of course, that layer also we tried just for the comparison purpose. And we did use the ply-by-ply model. That means every ply is represented by one element thick layer. Okay, like that. So ply-by-ply 16 plies. Then, of course, in LS-Dyna, there are large number of options are there. We use the node to surface contact option, and also hourglass option was used to control the excessive distortion. Okay, so also the density of bird volume was adjusted to have a weight of 165 grams. So if you remember the earlier requirement that I have stated, that is 165-gram bird hitting on a booster blade. So you can adjust the density of the bird so that and of course bird material, of course, there is a specific bird material that can be used. Uh, it's very soft. Bird is very soft. So the it is given in many literature is given the bird material that can be used as a soft material. Uh, velocity was varied from 50 meter to 150 meter per second to study the effect. Mesh sensitivity study was of course performed. That also we talk about, and smear property model was also tried. Performance was compared with the Plato-Prime model. Smear property model means like basically what we do is we average out the property of composite. Like let's say we have like quasi isotropic like 090 plus minus 45. So what you do is you calculate the average property of that whole thing 090 45 minus 45, and then put that average property for one particular element. That's it, and say that within that element all these four layers contain, and it's the average property of the four elements. That's called smear property. So that was also tried, and performance was compared with the fly-by-fly model. Of course, for of course, if you don't use the fly-by-fly model and you use the smear property model, so if you are interested only in the XYZ stresses and strain, then it could be fine. But when you talk about the interlamellar stresses and strains, then Snell property model generally can't give correct interlamellar stresses and strains. So for that, you need to have this Paper model. So we started with some preliminary results. So we did some um, blade analysis and also the plate analysis in LS-Dyna, and try to compare the results and location. So this is just a preliminary results. Okay, so as you can see, the maximum stresses and strains occur near the root of the blade. Same thing was observed in the FEA model of the plate also. Of course, X strain and interlamellar strains at different levels are shown. So here it looks like it's just a general model here. That's why the strain levels are interlamellar strain levels are very low because the general model. So then mesh sensitivity study was performed. So uh, as you can see here, different things were tried here. So the first one is of course smear property model. Okay. So here only three elements were used, and the properties of the composite were averaged out, and then those average properties were given to three elements. Even though it is a laminar composite, but averaging out the property and then giving two elements, the three element tick. So this is smear property model, and you can show the X strain and XG strain is shown. Now, as it is a smear model, yeah, as it is a smear model, you can see this interlamellar shear strain is very low. Okay, because that's what I'm talking about. In the smear models, our average properties, if you don't include the orientations and ply-by-ply different orientation, if you don't incorporate into the model, then the model becomes smear model, and then it cannot capture this interlamellar behavior or interlamellar stresses and strains. That's what it's showing here. Okay. Then again, there's another one. There's a force mesh. Another one more plate level. This is a blade, and this is a plate level model that's shown here. Again, it's low here. Then again, some different 16 plies model is tried here. 16 plies model that is showing the higher level of interlamellar strains. Then the root is thickened here. The root, if you thicken the root, then what is the effect of that is shown here. Then width of the blade. Suppose width of the blade is a little bit higher than what it shows. Oh, increase the width of the root. So at the root, the width was increased. So how much that effect that shows. And finally, ply-by-ply model 16 plies. So as you can see, if you see the ply-by-ply model, of course, interlamellar shear strain shoots up. Okay, that's the sign of the correct analysis. So of course, this is a linear static kind of analysis. So we are not incorporating any failure model here. Just we are trying to compare the different cases for applied load, how much strain is showing. That's what. Based on this, then uh, analysis of bird heat on the plate was carried out. So here, what it shows here is basically these are the different cases that we tried. If you look at the first case, so basically bird is hitting the plate at some angle, oblique angle. So as it is hitting the plate at some oblique angle, so we are actually dividing this velocity component into vertical and horizontal. So that's what it's showing here. The horizontal component and the vertical component. That's why the effective velocity is at some angle. Okay, horizontal component, vertical component. So that's the component velocity, and it is hitting on the blade, and angle at which it is hitting 32 degree, and where is hitting the bird location, bird impact location is near the tip. And then what are the strains that you are seeing? Axial strain, that is X direction strain, and interlamellar strain. These are the levels of the strain shown. And now we are trying to compute this parameter, that is interlamellar shear strain versus tensile strain. And just you just want to compare all these things in this parameter. So this parameter is calculated interlamellar strain over tensile strain. So that is showing like 0.84. Similarly, different cases, as you see, the velocity is varying here. The velocity is varying. Angle is same, but the velocity increasing here. Okay, as you increase the velocity, your strain levels are going up, and the ratio, you can look at the ratio now. The ratio is changing now. Okay, as the velocity increases, this ratio is changing, and ratio is actually, with the increased velocity, it is stabilizing actually. From 0.84 to it reaches to 1.4, and then it is getting stabilized to 1.4 only. Okay. Similarly, there are other cases like these three were like impact location is near the tip, then impact location of the bird mid length along the blade. Okay, so if I change the impact location, then what happens? Again, these velocities are changing, and as you can see, the ratio of intralamellar strain to tensile strain is also changing again. Okay. Then finally, again here, see, this is like 90-degree impact. This is 0-degree impact, and this is very obtuse angle impact, like kind of sliding over the blade. So these three cases were also tried here, and that also shows around this ratios here. So anything above 1.4 is a kind of promising case here. So that basically, what does it mean is if you are getting higher interlamellar shear strain, okay, that's good. Good in the sense that in general, these composite plates are going to fail in interlamellar way. Okay, so that means in realistically interlamellar shear strain should be high. So that means your ratio of interlamellar shear strain over tensile strain should be high. So as this ratio is high, the cases are correct. So these kind of cases where it is more than 1.4, these cases are assumed to be correct. Okay. Some more cases were tried, as you can see here. Here also, velocity is varying. Different velocities are tried here. Okay, and angles also varying. Sometimes the angles are 32 degrees, sometimes 90 degrees, sometimes 60 degree, and also the mass of the body is also varied here. You can see the mass of the body also varies. So based on all these cases, you can see that ratio is also changing here. In some cases, the like out of the bird mass, so here the ratio is going higher, 1.75, which is good. Here again 1.42. Okay. So yeah, so this is the analysis which was performed on the plate, which is 16-ply composite plate, and the bird hitting at different velocities. Okay. So learning from this simulations, what did we learn from this simulation? So uh, see, this is just initial part of the simulation, because initial plan, as I told you, plan was to carry out all the simulations, and then based on that design the specimen, and then do the testing on the actual specimen, and then again go back to the simulation and try to validate these experimental results with earlier simulations, and if necessary you run the simulations again and validate the results, and then from jointly from that experimental results and analytical FEA results, can we understand something what is going on, and then use those learnings for the design of booster blades. Okay, so yeah, so from this simulation, what did we learn? So to design a test configuration where there's a high probability of interlamellar failure than fiber breakage, which is the common failure under the strike. Okay, common failure means interlamellar failure should be the common failure. So can we design a specimen like that? For all the cases where interlamellar shear strain to tensile strain ratio is higher than 1.4 are promising. Okay. So then, based on those simulation results, we went ahead and decided to design a specimen. So, of course, the specimen length was 5 inch by 2.7. Total length is 7 inch, but the 2 inch is going into the tabs for holding the specimen. Okay, and then this just like a rectangular plate made of carbon composite with different layups like quasi-isotropic and actual family layup, and we'll be making this plate using autoclave, and then uh, hand layup and autoclave, and then cutting to the size by 7 inch by 2.7 inch, adding the tabs on it, and then putting the strain gauges on both sides near the base, and the bird is hitting at different locations. This is the bird is hitting either at this tip or somewhere in the middle, or maybe half the bird outside, half the bird inside, like partial bird hitting, like the different things we tried. And of course, the plate will be fixed at some angle to the direction of travel of bird. So to tell you that this testing site is at National Aerospace Lab, Bangalore, and if you go there, they have a very nice this bird hitting testing facility. So they have a big gun there, and you can shoot these gelatin birds through that gun at different velocities, whatever velocity you want, 50 meter per second to 100 or 200 meter per second. The bird goes at very high velocity, and like 10 to 20 meter away, there is a picture where you can actually fix the specimens at whatever angle you want, or whether it's a transverse to the direction of travel of bird, or it's some angle at direction of travel of bird, and then you hit the bird, and then bird hits the specimen, and then a nice facility there. NAL has a nice facility. So we designed the specimen, fabricated the specimens, and then we took the specimens to NAL, National Aerospace Lab, for bus strike facility, and gelatin bus were used and thrown at different velocity. Approximate bird size was like you can see 1.6 dia and 3.6 long and 110 gram bird like this. So this bird size can be bird size. Actually, the bird length there is no limitation, but bird diameter there are limitations of the gun. So 1.6 dia they are using right now. 1.6 in dia. They have some different. Not many options are there for diameter, but length can vary. And then, of course, we tried this 7-inch by 2.6, 16 by 16 ply plates, and with different layers. 10 specimens were tested, isotropic and handled layer. Yeah. Then, as you can see, this were the test results now. Okay. So, as you can see, we started from 66 meter per second bird velocity. Okay. And all these layers, these plate layers are fan blade, actual layers in the fan blade. Okay. So we are using the velocity of 66 meter per second and hitting the bird. You can see the strain gauges which were installed on the specimen on the compression side and tension side both. So as this blade is going to bend under the impact, so one side of course will be showing tension strains, and other side will be showing compression strains. So of course, so we try to measure those things, and as you can see, the level is the tension compression side strains are reaching the level of 1.2, 1.3 before the specimen fails. Okay, before the specimen fails, they are reaching like 1.3, 1.4 like this. Okay, so the interesting thing here is, as you can see, the first three trials, 66 meter per second and 71 meter per second, and first three trials, you can see that there is no damage in the plate. There is no damage in the plate. So bird went and hit the plate at that high velocity, 66, 71 meter per second, but it did not damage the plate actually. Okay. It did not damage the plate. So plate survived very well. Then you increase the velocity to 75 meter per second, and then you start seeing the damage. Okay. Yeah, increase the velocity to 75 meter per second, and you are seeing the damage. You see the damage like fiber breakage damage. Then again, you increase the velocity to 85 meter per second, and you see the combination of fiber breakage and delamination failure. Then again, you increase the velocity 90 meter per second, and then you can see fiber breakage, fiber breakage. Okay. So the interesting thing here is most of the time you are seeing fiber breakage here, but actually it should be delam. So the trick here is, can we change the setup to actually set up slightly, or can we change the velocities or direction of impact, something so that it fails into delamination kind of failure. Because that is the actual failure that pets will see. So here, this one particular case, it shows like a combination of power breakage and delamination. That's interesting. This was about the fan belt kind of layout. Then we went ahead and did some also kind of layout in the plate. So here also, if you see, 55 meter per second velocity, you see no damage. Okay. And then you start increasing the velocity 65, 68, 77, 83, 85, 92, like this. You go on increasing these velocities, and you can see that strain levels are changing a lot. Okay. They're reaching like 1.3, 1.7, 1.9. Strain levels are reaching high. And also the failure kind also is changing, failure type. So we can see like sometimes it's a combination of fabric plus dynam. Sometimes mostly it is a combination. Okay, but if you look at the case number 8, okay, that is showing clearly delamination kind of failure, so no fabric. Very interesting. The case number 8 is a delamination kind of failure, and why? Because it's the offset impact. I think offset means what they do is if you look at the figure there, yeah, here. Offset means the bird will be overhanging over the plate like this. Half of the bird is outside, half of the bird is inside like this, and then it's hitting like this. If you move this circle, let's say 1 inch on the left side, then how does it will look? Like that. That kind of offset impact. Okay. So in case of offset impact, of course, you because it is the plate is twisting, and then because of twisting, denomination mode is getting dominant kind of thing, and we are seeing the denomination kind of failure. Okay. So this is what happens. Then again, 69 meter per second, offset plus midline impact, offset impact. All the offset impacts are showing this denomination dominant failure. And these are the test pictures. As you can see, these are the real plates, composite plates, and there was a picture there, and you clamp the plate because plate is, if you see the tab there are tabs on the plate on both sides, plastic tabs, they are bonded. So you hold the specimen tightly in that area, in that region, like bonded region, and then you shoot this bird. And as you can see, when there is no failure, the top pictures are like very high-speed camera pictures, like the bird is hitting the composite plate and just sliding over it without causing any damage. The bird is hitting here, and the plate is bending a lot. Plate is bending a lot, but as the plate bends and finally the bird hits and passes away, there is no damage. So that we saw for almost 50 to 60 meter per second. Generally, there is no damage. If you remember here, yeah, no damage up to 71 meter per second. No damage. So that's what happens here. No damage. Bird hits and goes. But as the bird velocity increases beyond 71 meter per second, then you start seeing the damage. Now you are seeing the damage here because the velocity is high. So now you see the damage here. The plate is bending, and fiber breakage is also here at this near the base of the plate. You see the fibers are breaking here, okay, near the base of the plate. So this is what the failure is also here. This is for handmade kind of layer. Then of course quasi-isotropic layup also for some, let's say up to 55 meter per second, we didn't see any damage there. The birds are coming and hitting. Okay, but if you look at the velocity beyond 55 meter per second, then of course there is a fiber breakage and delamination is seen. Okay. Based on the location of hitting. See, here the location of bird hitting is shown here, but it may we vary, like sometimes it is near the tip, sometimes it is mid length, the middle of the specimen, or sometimes the offset bird. Offset bird means half of the bird is hanging outside, so only half bird is hitting on the plate and half is hanging outside the plate like this. That is offset bird hitting. So about the test analysis correlation, now we have the test results. Then we went back to the same plate level analysis, and we tried to run the exactly same velocity. Like for example, if we have got the test data for 55 meter per second velocity, quasi-isotropic, then we went back and did the same analysis on the quasi-isotropic plate model and 55 meter per second impact, and then we tried to match it. The strain levels. Okay, so here the funny thing is uh, the what we did is now we have to match the strain gauges variation. Okay, so the strain gauges, if you remember, they were fixed near the root. Strain gauges, tension and compression strain gauges were fixed near the root. So what we did is we took the same location into the FEA model. Like an FEA model, what we did is at that location of strain gauges where actual strain was measured, we consider that region where there are whatever number of elements are there in that region, we average out the strains, and then we try to compare with these strain gauges. Okay. So if you see here, this is the actual comparison of FEA and experimental here. Okay, at the strain gauge location. For this is what tension, and at the compression also, this is the actual comparison of strains at the strain gauge location. And at the root and the in the FEA, the max occurs somewhere else, not on the location where strain gauge is there. So that maximum strain also is plotted here. Okay, maximum strain near the fixity, that is also plotted here. Of course, that goes like wide variation there, goes like wide variation. But at the strain gauge location, we are getting the exact comparison for tension and compression gauges. Here in this case, the specimen did not fail. And then here in this case, specimen fell. So here also, if you plot the strain levels on the strain gauge location, then matches. But at the fixed location, the FA shows wide variation. At the fixed, of course, there may be many reasons for FA variation showing like this in the fixed location. Okay, but strain gauge location it does match. And here the specimen fell and it fell in the form of fiber breakage and delamination. Okay, so here also we see test for analysis correlation. This is for 75 meter per second. Specimen failure with the fiber breakage and delamination kind of thing. Here you see some variation in this stance. Then this is a fan bed actual layup that they are using, and here also you see the close match here. Okay. Then here also we see close match at 75 meter per second. The specimen fell in the form of fiber breakage and delamination. You see the close match here. Then 85 meter per second. Now here you see some variation here. Strange variation here. Strange variation at high velocity. So if you summarize these things like experimental strains and the FEA strains, you can see here like handled 3 velocities were tried. For subtopic, this so many velocities were tried, and you can see the experimental strains recorded on the strain gauges, and this FEA strains recorded at the strain gauge location. Okay, and these are the FEA strains at the other location, that is fixity location. Fixity means where the specimen is being held. So near fixity, it shows higher strains, but this is what it's showing now. These are the strains, experimental and analysis strains. Yeah. But of course, these are all tension and compression strains. There is no way we can measure these interlamellar shear strains onto the specimen. So that only if we can tell what is the interlamellar shear strains of them. So from there, then we actually went. That's what we actually went back into the FEA, and wherever they fell, specimens fell at the failure load and failure cases, we actually went back and found this interlamellar shear strain. So that's what. So this is that's what we are calling it as strain allowable. So what is the maximum strain that you see in the specimens when they are failing in the FEA? Okay, interlamellar and the acceleration strains. So at different velocities, as we see here, this maximum strain allowable you can see. So these are the strains we are seeing. So 2.4 to 2.4 to 2.5. That's what we are seeing strain levels. Of course, these are very high values compared to the static test. If you remember the static test, if you perform the static test on composite specimen, carbon composite, then you don't see that much high acceleration strength. But here you can see, because dynamic simulation, and of course the strain levels shoot up in dynamic simulations. So this is what it shows. So these are the dynamic simulation levels. Then of course this is standard layer. This is cross-isotropic layer. Here also you can see the strain levels. Average strain levels are coming like similar to 2.4 to 2.5 like this for the dynamic simulation. So where are we gonna use these things? Because what are learnings we have got, and we have found this strain levels. Okay, for the dynamic simulation. So next time the dynamic simulation perform in for any booster blade and composite booster blade and with the similar kind of loadings, then of course we can check that whether the strain level is reaching this allowable strain or not. If it's going beyond this, that means there's something wrong. So this one has to be designed in such a way that the allowable strain should be within these limits. Then we try to take the failed specimens and polish it up and see how they are failing. So as you can see, some specimens we did not fail. So we polish it up, and we saw there is no failure observed there, no interlaminar failure or no fibrobreaking, nothing. Side one, side two, nothing. Then when the specimen fails, then you can see actually the fibers are breaking here. The fibers are breaking here also. Fibers are breaking. You can see if you polish it up and see, you can see actually fibers are breaking here. Then this was actually this was actually family layout. Then quasi-isotropic layout. The failure is a combination of power failure and denomination failure. First specimen was like no failure, no failure, and the other side, the other specimen, when the failed specimen is C, you see the power breakage and some delamination also you see power breakage and delamination. Okay, in the specimen. Similarly, there's another quasi-isotropic specimen offset impact. There's offset impact. So side one, side two. So you can see that there's a delamination occurring there. Mid length offset, first specimen which is offset, second one is the offset impact, but middle length hitting, and this is like tip hitting, tip hitting. So you can see the denominations and all that stuff. Again, offset impact. You can see the surface denominations and internal denominations and uh, mostly. So whenever you are hitting the offset impact, of course the plate is trying to twist. The plate is trying to twist and with respect to the vertical axis, and that is why we are saying this denomination kind of impact, which is closer to what we want. So we have to design the plate in such a way that we get more of this kind of failure. So the conclusion of this work, different combinations of plate level bus track test and simulations were performed. Strain allowables for the material under consideration were obtained. Material in the sense the carbon composite epoxy IM78551, that for that particular material, and for these combinations of velocities and location of impact, we found these strain allowables. 70 to 100% higher strain allowable compared to that of under static test. So that is, of course, this is dynamic simulation. So in dynamic simulation, many things happen, and particularly in FEA analysis, you see that strain level shoots up a lot in dynamic analysis. So of course, I mean, these are allowables are for dynamic simulations only. And that is why next time somebody is using the dynamic simulation, we can use this strain allowables. The methodology is established here. More offset impact tests needed to develop the competence level in ILS allowables. And carbon fiber booster blades can be used in place of titanium booster blades. That's what the conclusion was. Properly designed composite booster blades are very much capable of taking the body impact. This was the conclusion here. Okay. Yeah, so Yeah, so that is what I have today. Any questions, please? Yes, please. Any questions? Hello. Any questions, please? Yes. Any question, please?
So participants, you can ask questions regarding today's FTP session. So anyone have a question? You can raise your hands.
Yes. Any question, please?
Yes, sir. We are waiting for that actually. I think no one turn up, sir.
Okay.
Uh,
Okay. Fine. Yeah.
so that's
Anyway,
a
anyway, if
nice
you have
presentation,
questions
sir.
later on, also you
Thank you,
can
sir. Thank you very much.
send any emails to me. My email address is here. Okay. Okay.
Yes, sir.
Thank you then.
Thank you, sir. Thank you very much.
Should I log out?
Yes, sir. You can, sir.
Okay, sir. Thank
Sure,
you.
yes.
Okay.
You can, sir.
Thank you.
Thank you, sir. Thank you. Okay. So participants, morning session, today's morning session gets over. Okay, na? So again, we will meet in the afternoon session. So the afternoon session starts at 2 p.m. Okay. Okay. Okay, participant. Thank you very much.